Fire, Gas, and Smoke Detection Systems Tutorial. Detector Selection and Application Integrity. A reliable fire, gas, and smoke (FGS) detection system begins with purposeful sensor selection, anchored in hazard severity, environmental demands, and integration performance. Detector technologies must be tailored not only to detect hazards early, but also to avoid spurious alarms and withstand operational stressors such as weather exposure, high temperatures, and mechanical vibration. Selection is not about device preference, but functional alignment with system resilience, fault tolerance, and diagnostic transparency. Maintaining detector integrity. Detector performance is sustained through deliberate attention to integrity, governed by the detection principle, calibration strategy, response consistency, and failure behavior. Best practices include choosing infrared over catalytic gas detectors for rapid, oxygen-independent detection and resistance to poisoning, deploying electrochemical sensors for H2S where humidity levels compromise semiconductor alternatives, ensuring all selected detectors are compatible with fire, gas mapping logic, and CL allocations, using acoustic detection only when ultrasonic background interference has been mapped and mitigated, avoiding reliance on unproven technologies such as early generation CCTV flame detection unless specifically authorized. Field experience, vendor reliability data, and system compatibility must guide every selection. Detector types like aspirated systems, open path IR, or ultra-sensitive smoke detectors must match site conditions, from pressurized enclosures to open atmospheric dispersion zones, application performance, and voting integrity. Every detector's contribution must be quantifiable within a system voting logic, most commonly 2N or 102D architectures. These logic schemes ensure that detection does not rely on a single point of failure, and that detector faults prompt safe defaults or redundancy fallback. Mapping tools must validate that each zone achieves a minimum defined detection coverage, typically 85%. That gas plumes or fire sources are not shadowed by equipment congestion. That performance under degraded states, one or more detectors failed, still meets safety thresholds. Mapping output should also identify undetectable zones, worst-case leak coverage gaps, and maximum credible gas cloud volumes between active detectors. System alignment and lifecycle support. The integration of detectors into FGS systems demands compliance with clear architectural and hardware guidelines. Detectors must support hardwired analog 0 to 20 milliamps or potential-free contact interfaces, diagnostic signaling for faults like beam blockage, fouled optics, or sensor aging, field replaceable sensors, and simple one-person calibration procedures. System integrity is enhanced when detectors are aligned with HMI design, providing meaningful feedback through both MMIC panels and DCS interfaces. Color-coded enunciation, voting feedback, and zone-wise isolation all support rapid decision-making. Conclusion: detector selection in FGS systems is not isolated procurement. It is safety instrumentation engineering. Each chosen device must meet defined detection goals, fail safely, integrate logically, and sustain performance under environmental and operational stress. When configured using mapping methodology, voting logic, and diagnostic planning, the result is a resilient detection system that actively supports plant safety and operational continuity. Selection of point gas detectors, application criteria, detector preferences, and threshold design. Point gas detectors form the front line of local gas release detection. Their performance is defined by how effectively they detect gas concentrations at specific physical points, typically near potential leak sources, enclosed volumes, or air inlets. The selection of point detectors requires careful consideration of sensor technology, alarm thresholds, response latency, environmental resistance, and compatibility with the system's analog input architecture. Technology preference and application suitability. Infrared IR absorption detectors are the preferred technology for most point gas detection applications. They offer superior immunity to poisoning, rapid response times, and reliable operation in oxygen-deficient environments, conditions where catalytic detectors underperform or fail. Catalytic Pellister-type detectors, although historically common, are now considered secondary and require principal approval before use. They measure gas concentration by oxidation, which produces heat detected via a Wheatstone bridge. This method is slow to respond 20 to 30 seconds, requires oxygen to function, and is highly susceptible to poisoning from airborne contaminants like silicone vapors or lead compounds. Technical selection hierarchy. Point gas detectors should be selected in the following order of preference. Infrared IR absorption type detectors, fast response and high fail safety, immune to H2S, silicones, lead compounds, minimal maintenance and stable zero drift, cannot detect hydrogen, alternative technology required. Catalytic combustion Pellistor detectors, only acceptable with poison-resistant elements. Require periodic calibration due to short and long-term drift. Drift from aging and temperature shifts. Output calibration needed if deviation exceeds less than 5% LFL. Must not be used in oxygen deficient or high H2S areas unless specifically approved. Acoustic leak detection, if configured for localized point detection, may supplement point detectors in ventilated areas where gas migration detection is difficult. Requires ambient ultrasound noise mapping to prevent false trips. Alarm threshold configuration. When using point IR detectors, low-level alarm, 20% LFL, high-level alarm, 60% LFL. Single threshold systems, 50% LFL, if only one alarm set point is configured. When catalytic detectors are used with principal approval, alarm levels should match IR settings, 20% LFL for low alarm and 60% LFL for high. Drift must be actively managed through periodic adjustment. Environmental and operational considerations. Point gas detectors should not be installed lower than 1 meter above grade unless specifically required to avoid water ingress or mechanical damage. When installed in difficult-to-access locations, permanent calibration fixtures should be added for single-person testing and maintenance. Key considerations. Placement near potential leak points, e.g., compressor seals, flange connections, valves. Avoid direct exposure to washdowns, wind gusts, and particulate fouling. Calibration gas concentrations must remain below 60% LFL. Detector integration requirements. Each point detector must integrate into the IPS using either analog 020 mA signal or potential free contact outputs as specified by the control system design. Line monitoring must be included to detect short circuits, open loops, and ground faults. Point detectors should support self-diagnostic outputs, including sensor end-of-life indication, beam blockage or optic fouling for IR types, poisoning detection, catalytic only. All changes in configuration or calibration must follow formal change control, and calibration events must be logged as part of the system's maintenance history and version control. Conclusion. Point gas detectors are essential to local hazard identification and must be selected and applied in accordance with environmental tolerance, response performance, system integration, and maintenance strategy. Infrared detection is the modern baseline, offering robustness and speed, while catalytic technologies remain legacy options requiring high-touch maintenance. Proper selection, spacing, and configuration ensure that detection aligns with the system's SCL and coverage targets, contributing to both operator safety and plant reliability. Infrared type detectors, performance characteristics, and application scope. Infrared IR-type gas detectors represent the benchmark for point flammable gas detection across industrial environments. Their operation is based on the absorption of specific IR wavelengths, particularly around 3.4 micrometers, by hydrocarbon molecules. These detectors compare a measurement wavelength absorbed by gas with a reference wavelength unaffected, producing a gas concentration signal that is inherently stable and resistant to environmental disturbances. Key performance advantages. Fast response time. Immediate reaction to hydrocarbon presence enables early mitigation. Poison resistance. Unaffected by silicones, lead compounds, H2S, or other common airborne toxins. Oxygen independence. Maintains performance in inert or oxygen-depleted atmospheres where catalytic detectors fail. Low maintenance. Minimal sensor drift over time. Calibration intervals are extended. Fail safety and diagnostics. Internal optics are monitored for fouling or blockage. Many models provide a 2 milliamp fault signal for degraded conditions. Superior sensitivity detects a broad spectrum of hydrocarbons including methane, propane, and heavier compounds. Limitations: cannot detect hydrogen or non-hydrocarbon gases. Alternate technologies must be applied for these gases. Some IR detectors may exhibit reduced response at extreme ambient temperatures. Product selection must consider these thresholds. Low alarm, 20% LFL. High alarm, 60% LFL. Single threshold operation, 50% LFL. For gas turbines, detection thresholds are relaxed to 15% and 40% LFL respectively due to improved process control and faster response requirements. Installation best practices. Avoid locations with heavy vibration or frequent optical obstruction. Use only in clean, dry air environments. Do not install where mist or condensation may form on the optics. Always ensure the sensor head is aligned and accessible for testing and diagnostics. Catalytic type detectors. Legacy technology with application caveats. Catalytic Pellistor gas detectors detect flammable gases by catalyzing oxidation on a heated bead, producing heat that unbalances a bridge circuit. Though historically widespread, their use is now conditional and increasingly limited due to significant operational drawbacks. Limitations and risks. Oxygen dependency cannot detect in oxygen-depleted environments, leading to hazardous underreading. Poisoning susceptibility, sensitive to H2S, silicones, halogens, and lead compounds, which reduce sensor life and accuracy. Slow response. Typical T90 response time is 20 to 30 seconds, compromising early detection and fast dispersing releases. High maintenance. Frequent recalibration needed due to drift caused by temperature changes and sensor aging. Drift and calibration management. Short-term drift, often due to ambient temperature swings or electronic instability, while 3% LFL is common. Long-term drift, result of exposure to gas concentrations and sensor aging accelerated in active leak-prone environments. Detectors must be calibrated using methane or propane air mixtures at 20 to 60% LFL. Any deviation beyond 5% LFL requires immediate adjustment. Deployment restrictions, use only with principal approval. Poison-resistant versions are mandatory. Non-resistant variants are prohibited unless explicitly approved. Preferred only where IR detection is not feasible and the atmosphere is reliably oxygen-rich and clean. Alarm thresholds, low alarm, 20% LFL, high alarm, 60% LFL aspirated gas detection, specialized application for inaccessible or hostile environments. Aspirated gas detection systems are engineered for scenarios where traditional point detectors cannot be installed, typically due to temperature extremes, confined access, or contamination hazards. These systems extract gas samples from protected zones and direct them to remote sensing units via sample lines and pumps. Typical applications: gas turbine enclosures, underfloor voids or cable trenches, high-temperature ducts and spaces, machinery enclosures with limited personnel access. System design considerations must include reliable sample pumps and tubing rated for process conditions. Sampling systems should minimize dead volume and be resistant to clogging or moisture retention. Periodic validation is essential to ensure sample transport efficiency and sensor responsiveness. Aspirated systems increase system complexity and must be engineered to prevent delay in detection. Operational benefits. Isolated sensing keeps sensitive detection electronics away from harsh or inaccessible environments. Adaptability. Sample points can be changed or extended without altering the core detector hardware. Limitations. Slower response times due to sampling transport lag. Additional failure modes, pump failure, line blockage, must be monitored and alarmed. Requires regular verification of flow integrity and suction efficiency. Integration requirements. Aspirated systems must be mapped into the IPS DCS with appropriate alarm delays and fault signaling. System performance and sampling line health must be included in preventive maintenance programs. In summary, point gas detector technology must align with the environmental and process demands of the installation. Infrared detectors are the primary standard for most hydrocarbon applications, while catalytic detectors are reserved for legacy or constrained use cases. Aspirated detection provides coverage where neither IR nor catalytic sensors can physically survive, but demands careful design and monitoring to ensure reliable operation. Open path gas detectors, extended coverage and perimeter defense for flammable gas detection. Open path gas detectors, also referred to as line of sight, LOS detectors provide continuous volumetric monitoring of hydrocarbon gas concentrations along a defined optical beam path. Unlike point detectors that monitor a single location, open path systems detect gas anywhere along their transmission path, making them ideal for perimeter monitoring, open process areas, and detection of gas cloud migration. These detectors operate using infrared absorption principles similar to point IR sensors, but on a macro scale. A transmitter emits an IR beam across the open area to a receiver or retroreflector. Any gas cloud intersecting this beam causes absorption of specific wavelengths, which is then interpreted as a gas concentration in LFL meters, LFLM. Operational advantages: wide coverage, detects gas across a linear path of up to 200 meters, significantly reducing the number of detectors required for large open spaces. Rapid detection, response is instantaneous for any gas entering the beam path. Early warning for migrating gas clouds, provides first-line defense before gas accumulates to hazardous levels. No requirement for local gas buildup. Detection does not depend on plume buoyancy or gas pooling at specific locations. Fail-safe diagnostics, self-monitoring for misalignment, signal strength, and optical contamination. Typical applications: perimeter monitoring of process units, jetty protection and inter-unit boundaries, open deck offshore platforms, fence line safety zones, zones where gas plumes are likely to migrate rather than accumulate, detector placement and range guidelines, offshore installations, 20 to 30 meters optimal beam length, onshore installations, 30 to 60 meters typical range, minimum operational range, 4 meters, maximum recommended range, 100 to 120 meters to avoid beam divergence and nuisance alarms. Beam alignment must be rigid and stable. Structures prone to vibration are not suitable for mounting. Alarm threshold configuration. Alarm levels are defined in LFL meters, LFLM, which represent gas concentration multiplied by path length. Low alarm, 1 LFL meum, e.g. 5% LFL over 20 meters. High alarm, 3 LFL, minimum recommended setting, 0.5 LF for detection sensitivity. Open path detectors can detect low concentration clouds spread over long distances or high concentration plumes over shorter segments. Design considerations and limitations. False alarm risk, long detection paths, e.g. 100 plus meters, may pick up transient, non-hazardous low concentration clouds. Alarm thresholds must be set accordingly to balance sensitivity and operational stability. Alignment sensitivity. Proper installation is critical. Beam deviation due to mechanical misalignment, thermal expansion, or platform movement can result in diagnostic faults or degraded performance. Environmental constraints, fog, heavy rain, and snow can attenuate IR beams. Modern detectors compensate with reference channels, but extreme visibility loss may still reduce reliability. Target gas compatibility. As with point IR, open path systems cannot detect hydrogen. Use only for hydrocarbon gases with known absorption spectra at 3.3 to 3.4 micrometers. Installation and maintenance requirements. Use vibration-resistant mounting brackets with alignment tools provided by the manufacturer. Ensure that both transmitter and receiver or retroreflector are accessible for cleaning and alignment verification. Include signal strength, trending, and fault outputs in DCS HMI for remote diagnostics. Periodically validate performance using certified test filters simulating LFLM levels. Maintain a clean optical path free from obstruction, e.g. dust buildup, plant growth, equipment movement. Optional integration and system logic. Open path detectors are typically integrated into the IPS via analog 420 mA outputs or digital relays. They must be mapped into fire and gas detection logic with consideration of voting requirements, e.g. 1UU2D or 2ON for zone confirmation. LOS detectors may be combined with point detectors to form complementary detection grids, enhancing both area coverage and local leak response. Conclusion: open path gas detectors offer expansive area coverage, early plume detection, and robust fault diagnostics, making them an essential component in any modern FGS architecture. When sited and maintained correctly, they outperform clusters of point detectors in open, ventilated environments, especially where early detection of gas migration is critical. Their deployment, however, demands thoughtful alignment, threshold tuning, and environmental compatibility to ensure lasting system integrity and reliable detection performance.